We'll now take up the last topic in digital modulations that is of interest to us, namely get a feel for the performance of Emery digital modulations. We have fully taken care of the binary modulations. The only thing left is Emery digital modulations. We have seen the receiver structures for Emery digital modulations, both for orthogonal as well as other Emery waveforms, Emery modulations based on two-dimensional signal constellations. Right? Today we like to take up the performance. Now, because of shortage of time, I will not be taking up detailed performance analysis of all aspects of Emery waveform performance, Emery digital modulation performance. However, I'll go through the broad approach, and also by now you are quite reasonably familiar with the techniques that need to be used, and I will be therefore leaving a number of things for self-study in this. So as we go along, I'll tell you precisely what you have to read yourself, although I'll be talking about the major result over here. And it will be very easy for you to do that because the basic ideas are similar to what you have been doing so far. Okay? So we'll take up then performance of Emery waveforms. And to start with, I'll take Emery orthogonal waveforms. And in this class of modulations, we'll consider the performance of the coherent demodulators or the coherent receivers. The analysis for the corresponding analysis for the non-coherent receivers will be very similar, and it will be very easy for you to work it out yourself, read it up yourself. Alright, now let's quickly recapitulate the decision statistic that we have to use for making our decisions for the case of coherent receivers in using orthogonal waveforms. That is, we are looking at what is the structure of the coherent receiver. I don't have the picture here, but it's very easy to remember that picture. You have a bank of match filters, right? And you are sampling the outputs of this bank of match filters at the time instant t equal to LT for the nth symbol, and depending on which match filter produces the largest value of this sample, you will decide for that particular symbol having been transmitted. Right? That is a structure that we have in mind, and the decision statistic, I did go through this maths at that time, but it's very easy to even intuitively remember what it was. The decision statistic is to look at the match filter outputs U sub m LT, right? The index m denoting the mth match filter, LT denoting the time index corresponding to which you are looking at the symbol. This will be equal to E sub p into delta m sub l m plus n m sub l, right, where m sub l indicates the symbol actually transmitted in the lth bit interval, right? M sub l also will take the values from 0 to capital M minus 1, right? So will m. The index m denotes which match filter output we are looking at, and m sub l denotes the actual symbol that was transmitted in that interval. So obviously this we'll expect this contribution from the pulse to come only in the m sub lth filter output, right? That's why this Kronecker delta function is appearing in this expression. And if we assume that the input noise is white Gaussian, then this match filter output noise as sample at this time instant will be a Gaussian random variable with variance N0 by 2, right? And also the noise outputs of all the M match filters would be mutually uncorrelated. We have seen that property earlier. Same white noise going through orthogonal match filters, the corresponding sample values of the noise variables that you will get will be all uncorrelated, independent. So we have already seen that for white Gaussian input noise NT, these random variables n sub ml prime are, and since they are Gaussian, they are also independent Gaussian random variables with expected value of n sub ml prime square being equal to n sub 0 by 2. Alright, this is the decision statistic based on which we can easily do our error analysis, at least in an approximate way. I'll only consider the approximate way here. There are both kinds of analysis possible. One approximate method, and the other more exact method. But the approximate method itself is reasonably good under certain situations, and also it gives some interesting insights. So I'll consider the approximate method first. What is the error event before we come to the method? The error event in this case is described as follows. Given that, let's say, a particular symbol M is a true index. I'm slightly changing the notation now, because earlier M was denoting the match filter output corresponding to the M match filter. But I'm now simplifying the notation, saying given that M is the true index, the transmitted index, right? The error event is that some other match filter output exceeds the match filter output corresponding to this index, right? So some other match filter output actually the real part of that exceeds the output of the mth match filter, right? This is a reasonable statement of the error event based on which we can try to compute the error probability. You all agree with this? The true index is M, but the largest output is not coming from the corresponding match filter but some other filter, right? The approximate method uses what is called a union bound method for calculation. Approximate evaluation of P sub B is based on what is called a union bound argument. The union bound argument is basically this: if M is your true index, then there is a certain probability that let's say we'll go through a count of all the other possible indices, leaving M, right? So we'll go through all the possible ways by which errors can occur. That is, M is the, let's say M is some non-zero value, or let's say M is the zero index, just for the simplicity of our discussion. Let's say M was 0, right? The very first index. Then the error event is that something other than the zeroth match filter is producing the largest output. The union bound says we'll calculate the individual probabilities that the match filter corresponding to index 1 produces output larger than 0. Similarly, we compute the probability that output match filter corresponding to index 2 produces larger output, and so on and so forth. And we just add up all these probabilities.
That will be pessimistic.
That's obviously a pessimistic answer, and it's an upper bound, right? So that is what the union bound does. It's an approximate method, and there is an error in it. We'll try to appreciate that. But have you understood the argument? The argument is that we calculate the probability of every one of the other indices producing an output larger than the match filter output, and the sum of all these probabilities is taken as the overall error probability. Right? This is not a true probability error probability calculation. This is an approximate calculation. That is, you're taking the union of all possible error events as the actual. The error event is being broken up into a number of events which, if disjoint, would have given rise to a correct result, but they are not really disjoint.
So we're not taking the union, we're taking the addition, because if we had taken the union, then it would have been exact.
No.
So we're taking
union and this thing disjoint.
So first of all, why aren't they not disjoint? So won't they correspond to?
Let's put it this way. It's possible that more than two match filters produce an output which is greater than your mth filter output,
So we simply
right?
Any
Whereas, so therefore what is going to happen is that is going to be counted twice in this situation, right? You appreciate that? Because this is also producing and that is also producing, and individually we are taking the probability of, we are only looking at one of them. We are not looking at this joint event at all.
So therefore it's an optimistic.
No, it's a pessimistic thing, because that is being counted twice. The probability
error probability
of each of these is being calculated individually, irrespective of the other. Right? It's being counted twice, and so on. It can, of course, theoretically happen that more than two also do it, but of course the probability of that is very, very small, so we don't have to worry about it. So that is the basic idea of the union bound. That is, you define, let's say, the conditional probability of this event. I'm going to denote by P sub m prime given m as the probability that the output sample of the m primed, this should be please read as m primed, okay, match filter is greater than the corresponding output of the mth match filter. Okay, given that m was transmitted, this indicates the probability that some other match filter m prime is producing a larger output than the mth filter. Alright, then what the union bound says is that the overall error probability will be simply the sum of all this for different values of m prime, not equal to m. So union bound tells us that P sub e is actually less than or equal to, because it's a pessimistic, the sum of all these conditional probabilities for m prime not equal to m. That's your union bound.
So this can be greater than one also.
How can it be greater?
Like if you sum in the probabilities, so we have no restriction that it has to be less than one.
Oh, it can be greater than 1.
Yes, sir.
Yeah, of course. A bound can be greater than 1, which is alright. Because after all, P sub e is going to be a probability, and probability is going to be less than anything less than 1 can also be bounded by something greater than 1. In that case, that bound will be useless, right? True, I agree with that, right? But let's see how useless or useful this is. Okay, so is the union bound argument clear to everybody? All right. So now this probability we already know, P m prime by m, given m. It's the same probability that we considered for the binary orthogonal case. I mean, instead of taking, we are essentially now taking a pair at a time, isn't it? So essentially it becomes the same question as if you are considering binary orthogonal scheme as far as one particular value of m prime is concerned, right? Therefore, Pm prime given M is nothing but, well, whatever result we got for the binary coherent orthogonal scheme, which was, I think, right? Remember, it was only slightly different from the corresponding result for coherent PSK, right? The 3 dB difference was there. So if you remember the form of one of them, you can write the result for the other. So this was the result that we did for binary PSK, binary FSK, coherent demodulation. Therefore, for Emery orthogonal waveforms, the union bound tells us, now this is going to be same for every value of M prime, and you're adding up how many terms? M minus 1. So it's going to be equal to M minus 1, less than or equal to M minus 1 times. You like to express this in terms of bit, average bit energy. Now we know that EP is, or EP by log 2m is your E sub B, right? So E sub B can be substituted by that, and this result becomes M minus 1. This should be in brackets, log 2m E sub B by N0. Okay?
You've written EP delta log m equal to EB.
Yes, EP upon log 2m, because it's the energy for k bits, k equal to log of m to the base 2. That's equal to the average bit energy, right? So that's a result that we get for the performance of Emery orthogonal coherent demodulations, making use of the union bound. Now this becomes an exact expression asymptotically. That is, as the signal to noise ratio EB by N0 is increased, this actually becomes a very close, or in fact an equal relation for EB by N0 tending to infinity, equality relation. Therefore the union bound is not too bad, right? Why it is so? Because after all, remember, what are the kind of events we did not consider? The events that simultaneously more than 2 match filters or more than 2 match filters other than M producing an output larger than M. That probability will become smaller and smaller as signal to noise ratio becomes larger and larger, right? And therefore that possibility of counting that twice or more than once, that becomes remoter and remoter, right? Therefore this becomes a true asymptotic expression for the error probability. Right? Of course, for smaller values of signal to noise ratio, there is a considerable amount of approximation involved, or for that matter, for smaller values of M.
So how do you correlate with M?
It's not directly correlated, right? But that's a finding.
Then how do you take it? P M prime given M is equal to Q of root of EP by N0.
Okay, this result, what I'm saying is precisely the same as, it has to be the same as what we obtained for the binary FSK case.
But now the distance between the two signals will matter.
Yes. Every signal has the same energy E sub P, right? Orthogonal waveforms. We are considering only a pair of orthogonal waveforms now, which is what the binary modulation scheme is, right? So there is no difference when you see, basically this becomes a pairwise calculation. M was transmitted, but M prime was taken to be larger, gave the larger output. This is the only event we are considering, and if you just look at this event, that's precisely as if you are only looking at binary FSK or binary orthogonal signaling. Okay? Any other doubts or questions?
So at high SNR, you mean this will approach an equality?
That's right. As SNR tends to infinity, asymptotically. When I say high, actually I am talking about an asymptotic result here. Alright. So what do you see from here? You see that what happens? Let's see what happens to error probability as M is increased. From this bound, what do we learn? It decreases or increases?
Increases.
As M increases?
It's coming inside also. So.
So it will become more and more exact.
So it will decrease.
Okay, we'll come to this point.
So because m is inside also and
Outside also.
factors.
So one has to see which one is more important.
I
Which,
think log 2n will dominate. Decrease the.
okay, the behavior will be different depending on what is the value of EB by N0.
EV by NG.
Okay, we'll see that. We'll come back to this question. Keep that in mind. In fact, I'll take up that question right away. Here is a plot of, but before I give the plot, let me talk about a little bit about the exact expression, which I will not do here. I'll leave that as an exercise for self-read. For Emery orthogonal system, the precise expression for the error probability is something very. It's an extension of what we did for the binary case, but the final result is this. It looks like a complicated looking integral. Okay. This is a more precise expression. Not readable? Okay, let me read it out for you. This, or maybe I can rewrite it. May not be able to fit into the space that I have available with me. Is it more readable now? This is where I get into trouble now.
So this n naught is not in the.
N sub 0.
So n sub 0 is not in the.
No, it is in the square root sign. Everything is under the square root. Okay. I think it is still messing up.
How does it come, sir?
This to the power m minus 1. This square bracketed expression to the power m minus 1. This is only the. Is it more readable now? Yes.
Excuse me, sir.
Yeah.
Put on the mic.
And they haven't even told me. All right.
So in this case it's 2 EB by N0. The earlier it was EB by N0.
Well, the final expression is not possible to get it in a closed form. It's again in the form of a complicated Q function. So you can't make out anything from this. You can't directly compare this non-closed form result with a closed form result. Okay. Approach is very similar to what we did for the binary case. It's just an extension of to that for the Emery case. So please read that. Okay. This I am leaving out for self-reading. It's something that you can easily understand. Therefore,
In the Photoshop you have not given
I'll give you that. I'll give you the notes. Now another result. All right, let me finish with this. This is a plot of this error probability. Okay. I plotted here for EB against EB by N0 for different values of M. So as you can see, as you increase the value of M, the curve tends to become lower and lower, provided you are above some EB by N0 is greater than some minimum value, okay, which is about minus 1.6 dB or something. Now this value is minus 1.6 dB. all these curves intersect at this point. Okay, so the answer to that question which I asked, sorry, the answer to the question that I asked you some time ago as to what happens to the error probability as m tends to infinity, the answer is that the error probability tends to 0 provided the EB by n0 is on the right of this point, that is this point is actually ln2, right, that is how it is minus 1.6, and it tends to 1 as if your EB by n0 is less than this value. So there is a threshold value of the signal to noise ratio. If you are above this threshold value of the signal to noise ratio, increasing m always improves the error probability for a given EB by n0. Okay, and this you can prove theoretically, and it's also proved in the book. I'd like you to read it up yourself.
So which book?
As a same book. Okay, and that's a very interesting result, remarkable result. I hope you appreciate that, because unlike what you might be thinking for Emery modulations in general, particularly when we talk in the context of let's say 2D Emery modulation schemes later, as we'll see, the error probability does not increase with increasing value of m, which you might expect to happen, right? But for orthogonal modulation schemes that doesn't happen because they are orthogonal, right? Because every time you add a new value of add a waveform, you are going into an orthogonal direction in the signal space. There is a price to be paid for it, right? Can you guess what that price might be? More in terms of bandwidth. It will be basically in terms of bandwidth. You are going to have to expand in bandwidth because you are adding newer and newer dimensions to your signal space. That means your signal should be such that it occupies higher and higher frequencies typically. Otherwise, it's very. I mean, this is of course not obvious from this discussion. I have not gone into bandwidth calculations at all, but it's something that one can appreciate to some extent because you are adding dimensionally to the signal space by adding more and more orthogonal waveforms. Then something has to be paid as a price, and that price is in terms of bandwidth.
Increasing
right?
dimension can be correlated with increasing
In bandwidth.
Exactly, you say the bandwidth will work. We are having
I have not given an exact argument because I have not gone into bandwidth calculation at all. But roughly, given a bandwidth, there are only a certain few number of waveforms that you can design which will be mutually orthogonal. You want to add some more waveforms, you have to necessarily go for higher bandwidth. Okay. So essentially, let's look at it only intuitively from that point of view, and therefore the Emery orthogonal modulation schemes are asymptotically very good as m tends to large values, but for a price which you may not be able to pay in real life practice. So that is something to keep that in mind. Now there is another related result here regarding simplex signals, which we have discussed before. Do you remember what was the motivation for introducing simplex signals?
antibody. There is more distance between the
Energy being reduced.
more
Average energy.
The motivation was, and this is a result now you can prove, I like you to read it yourself, that it will yield you an Emery simplex set of waveforms with the optimum receiver, coherent receiver, will yield the same error probability, same error rate as the orthogonal set with an average energy which is less. Okay, and the relationship is that average pulse energy will be 1 minus 1 by m into E sub p rather than E sub p. So if E sub p, the energy of the pulse required for a given error rate is E sub p for the orthogonal case, it will be this value for the simplex case. Of course, as m tends to infinity, as m becomes larger and larger, this difference becomes smaller and smaller. Okay, so asymptotically with m, both have similar performances, but for a finite m, simplex set holds an advantage over the orthogonal set. Okay, so this result again, I like you to read from the book yourself. It's a fairly simple proof and you can easily appreciate it. Finally, before I leave orthogonal signals, let me discuss one point regarding the error rate calculation. The error rate calculation that we have done so far is with respect to symbol error rate, right? It will be an interesting question to ask, how is the symbol error rate in this case related to bit error rate? No, don't jump to conclusions, just think about it.
So bit error rate will be 1 by log 12 because if we use grey code then there will be 1 bit in error.
There is no particular significance of grey code in Emery orthogonal signaling. It's very important for two-dimensional Emery signalings, right? But for orthogonal signaling, because everything is orthogonal to everything else, right? There is no nearest neighbor as such. Every orthogonal waveforms is as close or as distant from every other waveform as any other. There is no preferential distance relationships, right? The distance is precisely 0 in terms of orthogonality, right? So there is no significance of a grey coding this thing for the orthogonal schemes. So don't jump to conclusions therefore. So what can we say about bit error rate, bit error versus symbol error probabilities? Now let's leave the world of speculation and try to see what result we can get. Now let's go through some logical arguments. Now the first point is, when a symbol error occurs, any one of the other m-1 symbols could be obtained, right? The erroneous symbol could be any of the other m-1 symbols other than the true one. That is the first thing to appreciate, right? So a symbol error implies the erroneous symbol could be any of the other m-1 symbols, right? Also, this probability of going from causing the symbol error, the probability of a particular symbol error is going to be same no matter which symbol I consider, right? Whether I consider the index m as the true index, m equal to 0 as the true index, or m equal to 1 as the true index, or so on, this symbol error probability is going to be same because all the waveforms are symmetrically placed with respect to each other in the signal space.
So then they assume that the distribution also is the same probability.
Assuming also that the a priori probability is also same. All symbols have same equal a priori probabilities, right? Therefore, the second point to appreciate is that this probability is independent of the particular symbol transmitted. Right? That is, it doesn't matter what is the true value of m. Therefore, I can take a convenient value of m for which I can do the calculation more easily, and then the result will hold for any other value of m. Okay, because of the symmetry of the problem, it doesn't matter whether I do it this way or any other way. All right, a convenient value of m to consider is m equal to 0, all zeros, right? Or the index m equal to 0, which will correspond to a k-bit word of all zeros, right? So choose m equal to 0, and the binary k tuple implied by this is a bit sequence of all zeros, let's say. Then the erroneous words, the possible erroneous words, are all the other possible words, right? Because this is the true value, all the error values will be m equal to 1 to m minus 1, and that will correspond to all other bit sequences other than the R0 bit sequence, right? Therefore, I can now count how many different error patterns exist, right? For example, if the error pattern corresponds to m equal to 1, then this is 0 0 0 0, let's say 1, and only one error occurs, right? If it is something else, two errors may occur, depending on what error pattern, what value of m has been actually selected, all right? Therefore, the average number of bits that can go in error will depend on what is a decoded word. What I can do is I can count the number of ones in all the other words, right, and divide it by m minus 1. That is the average value, average number of bits which can go in error, if there is no specific preference for one over the other, all right, on an average. That's a basic idea. So fix any symbol which we have done, choose m equal to 0, and let's say expected number of errors per symbol. I think I should say bit errors. Expected number of bit errors per symbol is nothing but the expected or average value, average number of ones in all non-zero symbols, right? So I have to just count the total number of bits, total number of ones in all the non-zero symbols. And divide by m minus 1, right? Now it's very easy to check. This is an argument that you can, just have to sit down and do it and verify that one can count this total number of ones in all the non-zero symbols as equal to half k into 2 to the power k. It's in fact obvious, right? Because the maximum value is k, the minimum value is 0, average value is k by 2. The minimum value is 1, average value is k by 2, and there are 2 to the power k minus 1, sorry, 2 to the power k such words. So that is something that you can verify more precisely, divided by m minus 1, and substituting for m, one can write this as equal to k times 2 to the power k minus 1. I am writing this half of 2 to the power k as 2 to the power k minus 1, okay, divided by 2 to the power k minus 1, right? This is therefore, what is the significance of this? This is a figure which tells me what is the average number of bits that will go wrong when a symbol is wrongly decided, right? That is, out of k bits that are present in the word, so many bits will be on an average wrong. Clear? Therefore, what is the bit error probability? Divide by k, right? Clear? This is the number of bits that will go wrong for every k bits, every group of k bits. For per bit, the error probability, bit error probability, which I will denote by p sub e comma b, will be 2 to the power k minus 1 upon 2 to the power k minus 1 into p sub e, which is the symbol error probability, which is what we have calculated earlier. Okay. So that is the connection between bit error probability and symbol error probability.
So how do we measure out the k?
I have divided by k. Why? Because this is the average number of bits that will go wrong for a group of k bits, isn't it? For per bit, the average number of bits that will go wrong is divided by k. It tends to half provided your k is very large. right? If m becomes very, very large, then bit error probability is precisely half of symbol error probability. Okay, quite true. Okay, all the rest of the results concerning Emery orthogonal signaling, namely the exact result, the corresponding result for the simplex family, and the non-coherent receiver results, they are very similar in nature. I like you to study on your own. Okay, the detailed behavior is also similar to what we have discussed earlier. So read everything else regarding Emery orthogonal signaling. For example, non-coherent receiver error calculations. Okay, because I would like to finish with this topic today. Yes. Okay, finally, let me come to error rates for Emery signal constellation. When I say this, I usually imply automatically that I am talking of two-dimensional signal constellations, right, which are very popular. The reason why they are popular is because one does not expand in bandwidth as one increases the value of m. The bandwidth is more or less fixed because you are using the same pulse shape no matter what is the value of m, and therefore the bandwidth is under control. Whereas in an orthogonal signaling scheme, one has to necessarily design a group of waveforms which are orthogonal. So more than one pulse shape is involved. In fact, m pulse shapes are involved, and the combined average bandwidth of all these m pulse shapes will be quite large, right? In fact, that is a price which may be at times very difficult to pay. That is the reason that you will find very rarely Emery orthogonal schemes for very large values of m under practical use. Okay, although theoretically they are of great significance. Okay, so let us return to these two-dimensional signal constellations, where we use, if you remember, basically a single match filter, right, and then the IQ outputs of this complex match filter are decoded to find out which symbol was actually transmitted, because depending on which decision region it lies in, right, because the two-dimensional signal space is divided into a number of decision regions. Each decoded point will lie in one of these decision regions, and our decoding strategy, demodulation strategy, is to choose the symbol in which corresponding to the decision region in which the point actually lies, the complex output actually lies, right. Let me recapitulate the maths for you. The match filter output before sampling is some waveform like this. We are using a single match filter, either at passband or at baseband. Okay. Then if it is a Nyquist pulse, that is an assumption that we have always been making, then your ULT is going to be equal to A sub L plus n prime, let us say n prime L. Okay, because the only contribution that will come is from the Nyquist pulse in the corresponding interval, the interval from LT minus 1 to LT. Alright. So AL is your a point in the signal constellation that you actually transmitted, right, and this is coming along with complex Gaussian noise, or in other words, this is actually complex variable. It has a real part and imaginary part, both are uncorrelated, therefore it has a Gaussian distribution with zero correlation coefficient. Okay. So UL is the sum of, it's a complex variable which is the sum of AL and LL prime. This is a point in the constellation, signal constellation that was transmitted in the lth symbol interval, right, and this is a complex valued Gaussian random variable, and each component of this complex variable has a variance of sigma square or n0 by 2. Okay. Therefore, what can you say about U sub L? Let me write this as U sub L. It's a complex Gaussian random variable whose mean is A sub L, right? So therefore, suppose we have m possible symbols, there are m possible density functions defined for each of the possible transmitted symbols, right? Let me illustrate this for the case of, let's say, an 8-phase PSK system. That is an example of a two-dimensional signal constellation of this kind. So we'll have a situation like this. Okay, for 8-array PSK. These are the 8 points in the signal constellation diagram lying on a circle, right? And around each of these mean values we'll have a two-dimensional Gaussian density function coming up, which describes the density function of U sub L, right? Essentially this density function is imposed by the presence of the noise n sub L. And what we have to understand is now how we will do the error calculation for this kind of situation. Of course, I will do this exercise simply for 8-array PSK. I will just tell you the result for general two-dimensional modulation schemes. I don't think we have time to complete this, even this today, so I will start from this and quickly finish this next time, and then go on to the next topic that we will be taking up is a brief introduction to information theory and coding.